All right, now the final thing for 4.6 is we're going to talk about orders of magnitude. Uh, Whenever one quantity is about 10 times larger than another, we say it's one order of magnitude larger. So, ignoring the rest of that first paragraph, um, let's go down to this definition here. Given two values a and b, to determine how many orders of magnitude a is greater than b, the difference in orders of magnitude is log of a divided by b. let's look at a fast example. In a previous problem that we didn't go through, but in a problem that's in the textbook, we had some b that corresponded to 10 squared, or 100, and a c that corresponded to 10 to the fifth, or 100,000. And the question here is, how many orders of magnitude larger is c than b? Well, this is just going to be log of c over b. This is log of 10 to the fifth over 10 squared, which is log of 10 to the 5 minus 2 is 3. Then this is 3. So 100,000 is 3 orders of magnitude larger than 100. We also have earthquakes. I'm going to talk briefly about earthquakes because another example of logarithmic scales or of a logarithmic scale is the moment magnitude scale, which is used for earthquakes. This is not the Richter scale. This was actually the Richter scale was succeeded by the moment magnitude scale. So for an earthquake with seismic moment S, which is a measure of earth movement, the MMS value, or magnitude of the earthquake, is M equals 2/3 times log of S divided by S naught, where S naught is equal to 10 to the 16th, and that is a baseline measure for seismic movement. Looking at an example of how to use this. If one earthquake has an MMS magnitude of 6.0 and another has an MMS magnitude of 8.0, how much more powerful is the second earthquake? So for the first earthquake, we can find the amount of earth movement for that quake. So we'll call that S sub 1 instead of just S. This will be the amount of earth movement for the first earthquake. So we'll see here, we're going to have 6.0 is equal to 2/3 times log of S sub 1 divided by S naught. So this is just coming right from our formula for moment magnitude scale here. Instead of S on the top, I'm writing S sub 1 to denote the seismic movement of this 6.0 earthquake. Let's see, I can multiply both sides by 3/2. Let's see. Multiplying by 3/2 is the same thing as multiplying by 3 and dividing by 2. 6 times 3 is 18, divided by 2 is 9. This is equal to log of S1 divided by S naught. Exponentiating both sides, I get that 10 to the 9th is equal to S sub 1 divided by S naught. Multiplying both sides by S naught, I get S sub 1 is equal to 10 to the 9th times S naught. This means that the first earthquake is has 10 to the 9th times more earth movement than the baseline measurement. Let's find the same for our second earthquake. We'll call this S2 instead. So our equation now is 8.0 equals 2/3 times log of s sub 2 divided by s naught. Again, multiplying both sides by 3/2 to cancel is 2/3. I get what? 8 times 3 is 24 divided by 2 is 12 equals log of s sub 2 divided by s naught. Exponentiating both sides, I get 10 to the 12th power is equal to s sub 2 divided by s naught, or that s sub 2 is equal to 10 to the 12th times s naught. Now comparing the earth movement of this to the earth movement of the first earthquake, I can do s sub 2 divided by s sub 1. This is 10 to the 12th s naught divided by 10 to the 9th s naught. This is 10 to the 3rd, which is 1,000. So the second earthquake had 1,000 times as much earth movement as the first earthquake. And one more example. One earthquake has a magnitude of 3. If a second earthquake has twice as much earth movement as the first earthquake, find the magnitude of the second earthquake. Okay, well, the first earthquake has a magnitude of 3, so 3 is equal to 2/3 log of s over s naught. If I wanted to solve for s here, I multiply both sides by 3/2, like 4.5 on the left-hand side equals log of s over s naught. Exponentiating, I get that 10 to the 4.5th power is equal to s over s naught, where that s is about, or s is equal to, not about, right? 10 to the 4.5th times s naught. So the second earthquake had twice as much earth movement, we were told. So for that second earthquake, we instead have that s is equal to 2 times what we had previously, which is 10 to the 4.5th s naught. And if I wanted to find the magnitude of this would be m equals 2/3 log of 2 times 10 to the 4.5th s naught divided by s naught. This gives me that m is equal to 2/3 times log of 2 times 10 to the 4.5th. And if I plug this into a calculator, I get about 3.201. So the second earthquake will with twice as much earth movement will have a magnitude of about 3.2. And this is it for section 4.6.